rectifiers. Till now we studied about the PN junction. So we call the PN junction. In general, what we can say, when a diode, so P and N junction can be represented by a simple, that is a this is the layered picture of a diode. So this is a symbolic representation of the diode. So this we call it as a PN junction. Till now we studied about the PN junction and the breakdowns which occur in reverse bias also we studied. Now what is that PN junction? In normal we say PN junction is nothing but a diode. So this is a symbol of diode and this is a layered picture of a P and N material. So in between them a junction will be there. So if we connect a anode terminal to the positive and cathode terminal to a negative, we call it as a forward bias. If we connect a anode terminal to the negative side and a cathode terminal to a positive side, we call it as a reverse bias. When anode potential is higher than this cathode potential, we call it as a forward bias. Similarly, here anode potential is higher compared to the cathode, we call it as a reverse bias. So in general, what we can say, forward bias, we are dealing about the semiconductor devices. So these semiconductor devices are like a switches. When they are conducting, they are, that is nothing but a, for example, in case of a forward bias, we studied the VI characteristics of forward bias. As voltage increases, the current will also increases, that is in exponential way it will increase. In reverse bias, what we said, the current is very less. In general, for ideal case, we consider it as a reverse bias as a open circuit or a off state. So when it is forward bias, so that is represented by a short circuit one line with a conducting material. So that it indicates that point is conducting. So anode to cathode is short now. So when it is reverse bias, that anode to cathode terminal, we represented it by a open circuit. So this is the open circuit of this anode and cathode. And resistance offered, when it is conducting, the current is flowing, the resistance is minimum. Resistance and current are inversely proportional. So when it is open circuit, no current is flowing, resistance is maximum. And what about the voltage? When it is conducting, that is, if we draw the waveform of a conducting and well non-conducting, when it is not conducting, the voltage is maximum. When it is conducting, the voltage is minimum and current will be maximum. Similarly, when it is not conducting, current is 0. So these are the terminologies which you need to remember in plotting the graph. That is, when it is in forward bias, that is nothing but a short circuit. When it is reverse bias, that is in open circuit. So this is the layered picture of a PN junction. The voltage, that is the barrier potential voltage, that is represented as a V0. That we here in further discussion, that is represented as a E0. That is, E0 is nothing but a offset voltage, that is a junction voltage. Now in detail we are studying about the particular PN junction, that is nothing but a diode. So now ideal case of a diode. Ideal case of a diode in the sense, here in case of a forward bias as well as in case of a reverse bias, that IV characteristics we have to draw now. In case of a ideal case, so based on this only, ideal case when it is in forward bias. So how we need to draw the graph? When it if we draw with respect to voltage on x-axis and current on y-axis. So when it is forward bias, so the resistance is minimum and voltage is minimum. So voltage is minimum, that is in ideal case, the current is maximum. So that is represented over here like this, ideal case. Similarly, a reverse bias characteristics also we need to draw in the IV characteristics only. So in a reverse bias characteristics, what is there? Voltage is maximum, current is almost 0. So that is represented like this. Understood, no? This is the VI characteristics both in forward and reverse bias. So here it is forward bias. and here it is reverse biased. That is explained in the first condition. So when it is when we apply the forward voltage, the voltage when it is conducting in the sense, that is short circuit. So short circuit in the sense the voltage is 0, the current will be maximum. So this one is an ideal case. So ideally there won't be any drop, there won't be any resistance, but practically it will be there. So ideal case we are considering, and the reverse saturation current, that also we are neglecting in the reverse bias. So the reverse current is also 0, only the reverse voltage will be there. So this one is the ideal case, that is represented like this. So always current flow from, if this is the P and N junction, the flow of electrons is considered as a current flow. So the current will always flow from P to N. P to N. Again, conventional current flow direction is same as the whole direction. Now, ideal diode with offset voltage. So offset voltage is here, this is the diode symbol, and along with that offset voltage is represented over here. So this offset voltage is nothing but a junction potential. If this is a P and if this is a N layer, a depletion layer will be generated. So that potential is nothing but in previous case we represented it as a V0. So now onwards that is represented by a E0. So that potential we call here as a offset potential. So for this condition, so this is the ideal graph. This offset voltage, how we can explain with this offset voltage? For example, if we consider if we connect one voltage source for this one, so when it will be in a forward bias, here anode is connected to the positive terminal and cathode is connected to the negative terminal only. But also when this, for example, our offset voltage is 2 volt, assume it as a 2 volt, and our supply voltage is a 5 volt. So when I start to increase my supply voltage up to 2 volts, it won't conduct. So at the beginning my supply, as I increase the supply voltage, that is from 0, 1 and 2, if I start to increase, so when I apply a 0 voltage, what it says, anode is at a lesser potential compared to the cathode voltage. If I increase up to 1 voltage, then here it is 1 volt and here it is 2 volt. Again anode is at lower potential to the cathode, so it won't conduct, no current flows. Similarly, when it becomes a 2 volt, it won't conduct, both are at same potential. When it increases above this one, for example 2.1, 2.2 and 3 volt, so at what says 3 volt is greater than the 2 volt, that is anode is at higher potential compared to the cathode voltage. So at that time it will conduct. So up to the barrier potential, up to the this E0 offset voltage, it won't conduct. So the current will be 0. After that it will start to conduct, the same condition. So current starts to increase, and in case if you operate the same diode in the reverse bias, offset voltage it won't play any majority role in case of a reverse bias. For that reason that is not represented over here. And in a reverse bias condition, current will be, it acts like an open switch, no current flows, only the reverse voltage will be shown over here. Now the third case, ideal diode with offset voltage and resistance. So now ideal diode with some offset voltage, that is the junction voltage, and some resistance. So the characteristics in the reverse bias, it remains same, that is no current flows, because it acts like an open circuit. Reverse bias is nothing but an open circuit, no current, only the applied voltage, that is we are applying in reverse bias, only the reverse voltage. So up to E0, if you operate the diode in forward bias, up to E0 it won't conduct, after that it will starts to conduct. But here we are getting the VI characteristics in a slope manner, a slightly a bent curve. So why we are getting this one is because of rate of change of current that is happening because of this presence of this resistance. Now actual diode. So these are the ideal cases whichever we studied, no, the three graphs. So the now actual diode. So actual diode, there will be a resistance will be there, drop will be there. So for that reason, reverse saturation, that is when we operate the diode in reverse bias, then small amount of a reverse leakage current that will flow. So that current is also represented over here. Igen, that is nothing but a drift current because of the presence of a minority charge carriers in opposite junction. So that is represented over here. So all these three as well as this one actual diode graph, we call it as a piecewise graphs. So in exam they may ask about the rectifiers and a piecewise explanation of equivalent circuits. So in exam we have to draw all these four graphs along with the diode circuit and current direction and offset voltage. So here there is one more term, that is approximation is referred. So if we move from towards the left side, that is the ideal case, the circuit remains simple, so it looks like a simple. So when we move towards the right side, that is if we go more accurate, then the simplicity will decrease, that it indicates. So you can see from the ideal graph how it looks. The ideal graph and the actual graph, how it looks. There is a huge difference because of the drop and because of the offset voltage and the resistance which is present in the diode. Now application of PN junction. So this topic will come under rectifiers only. The first application is wave shaping. The first one is a wave shaping. This involves alteration of AC signal by passing only certain portion of signal while blocking other portion. As name says, wave shaping. So there are some applications of diodes where, as name says, diode is a unidirectional device, either by applying a forward voltage, either by applying the reverse voltage and that offset voltage. So we can change the waveforms as per the required application. So that is possible. So that is a one application of the diode. Then second one is a rectification. So as name says, rectification, the topic itself is a rectifier, that's the main concept. So it will allow only the positive. So when we give if this is a diode for this circuit, if we apply the input AC, then it will allow only the it will conduct only in forward bias. That is when we apply the positive voltage, then only it will conduct. So the voltage is shown over here in the output. This is output, input voltage, and this is the output voltage which is observed over here. You can see the magnitude. Magnitude is little less compared to this one because of the drop. That lesser value of input voltage is shown over here. That is this part. So this is the rectification process. So we call this as a pulsating DC. So if you want a accurate DC, if we apply this pulsating DC through filter, then we get the accurate DC waveform. So this is the actual rectification process of a diode, the main application of a diode. So now, as we said, PN junction as well as a rectification, there are few factors that will affect the performance of the rectifier. So in that first one is a band gap. So band gap is nothing but, we already studied in first module. This is valence band and this is conduction band. The gap between the valence and conduction band, we call it as a band gap, that is EG. So if EG, this gap is large, then offset voltage, that is a if we consider this as a PN junction, if the PN junction gap is large, means the offset voltage will be more. If the offset voltage is more, then more amount of a reverse voltage is required to occur breakdown because of the large depletion region, and reverse current reduces. So that is band gap. For example, if the band gap, as you can see here, if this gap is large, means what we can say, more amount of a temperature is required to excite electrons from this valence band to the conduction band. As well as a EHP, if the gap is more, means EHP pairs which are generated is less. So for that reason, when there is a large gap, so that will also affect the process of rectification. For example, for this power rectifiers, power rectifier in the sense when a diode operates at higher power, that we call it as a power rectifier. So silicon is generally preferred compared to germanium. Why? Because silicon has a wider band gap compared to that of germanium. So that is band gap. So band gap, if a band gap is more, then temperature required to raise the electron from the one place to the, that is valence band to the conduction band is more, as well as supply voltage required for the conduction is also more, and because of that reverse voltage will also increase, as well as the offset voltage is also more, and the reverse saturation current will be less. So that is band gap. The next one is doping concentration. The second factor which affect the rectification process is doping concentration. So we call this as a device dimension also. So you will get to understand why we call this as a device dimension. So here one figure is shown, that is a P and N junction, and here also one P and N junction is shown over here. So I told you, if a P is represented like a plus symbol or the N is represented by a N plus symbol, what it indicates? They are heavily doped. So here in the first figure, P is heavily doped compared to N region. In the second figure, P is lightly doped compared to the N region. So if a device is highly doped compared to the lightly doped, then the depletion width will be more because of this higher doping capacity. So they will penetrate towards the N region so deeply. So that's why here in a lightly doped region, the depletion region is more. You can see here, this one is highly doped and this one is lightly doped. Because of that, depletion region will be more over here compared to this depletion region, because charge carriers in N regions are less. So the depletion width will be less in case of P region. So what we can similarly for the right side figure also. In the right side figure, what it says here, N is more doped compared to the P region. So we consider only this P and N, heavily doped P region. So if P is more doped, then what it says, charge carriers are more. If a charge carriers are more, then current is more. If a current is more, what we can say, resistance will be less compared to this region. Here the charge carriers are less, and because of that current is also less. If a current is less, what we can say, resistance is more for this particular region. If the device is lightly doped, then the resistance offered is more because the charge carrier concentration is lesser. So if the resistance is more, what we can say, there is one term, that is I square R losses will be present in particular one junction, particular one layer of the PN junction. So this concept will come into picture, that is I square R losses, that will be in the form of heat. So how we can reduce this I square R loss? The term which we can control over here is the resistance value R. So we know the formula, basic formula, R is equals to rho L by A. Here by decreasing the length, in order to reduce the R, what we have to increase? We need to increase the length value, as well as we need to reduce the area value. So in order to reduce the R value, in order to, what we have to do, we need to reduce those losses, that is the heat losses, I square R losses. So how we can reduce the R value? By decreasing the L value. So how we can reduce R value? By decreasing the L value and by increasing the area. So then only I can reduce the R value. So this is another method, that is another factor that will affect the rectification. So the second factor that affect the rectification, we call it as a device dimension or device geometry. It will also plays an important role in doping concentration. So here in the handwritten, whatever I explained is for understanding purpose. Along with this, you have to write the theory also. Here is a textbook theory which I pasted over here. Go through the theory. So this is also the theory of particular explanation. The third factor. So the third factor which affect the rectification, the first factor which affect the rectification is band gap, and the second factor is device dimension, and the third factor is punch through as well as a premature breakdown. So again we call this as a doping concentration only. So how that doping concentration plays an important role in the third factor is, consider a heavily doped P region and a lightly doped N region. So if the P region is heavily doped, what it says, the depletion region in the N will be more compared to the P region. So where we have a more depletion region, that is in the N region compared to the P region, because N is lightly doped. So here, to explain this topic, we consider heavily doped P region and lightly doped N region. So what happens sometimes if I apply the reverse voltage? So what happens if I apply the reverse voltage? So the charge carrier will gain energy such that the depletion region will penetrate throughout this N region. So what it says, if this is our P region and this is our N region, if this is a depletion region from the N side, so the same depletion region from P side means it, because of the applied voltage as well as a heavily doped region, so the depletion region will penetrate throughout this. So that is nothing but a punch through. Depletion region penetrate so deeply in the N region, so that term we call it as a process, we call it as a punch through. So that is the one thing. Because of this punch through, what happens, if this is the VBR is the reverse breakdown voltage of this particular PN junction, so it will, that reverse breakdown voltage, it will break down at the lesser value of voltage itself. You can see from the graph, because of this punch through, what will happen, the device will break down at a lesser value of VBR. So this VBR is a prescribed value that will be specified by the manufacturer. Because of this punch through process, so what happen, premature breakdown will occur in the particular PN junction. So how we can avoid that premature PN junction? That is, first one is by beveled edge and by guard ring. Two methods are there, beveled edge and second one is the guard ring. So what is beveled edge and what is guard ring? That is explained over here with this picture. Beveled edge. So here you can see N plus as well as a P region. So this is the what we can say, side view. Okay, side view of this particular PN junction. So this is a beveled edge. So like this. So here, this is the side view of this particular PN junction. The beveled edge is nothing but it won't be exactly a rectangular, but it will tilt at the edge. So that we call it as a beveled edge. So this is the again side view of the PN junction, that you can see if a N is heavily doped, here they consider N as heavily doped and P as a lightly doped. So because of this beveled edge, we can avoid the punch through. Before this, if the beveled edge is not present, then what will happen, this N plus region completely penetrate through the P region. So that can be avoided by this beveled edge. So you can see from the figure itself, if we make a beveled edge, what happens, then the area at the P junction is more compared to the N region. So that electric field won't play any role over here. So that is a one way of reducing the punch through, so that we can avoid a premature breakdown. So the first one is beveled edge. Beveled edge is nothing but it will not be in a rectangular shape, a slight increase in the edges of the both side. So then second one is by guard ring. So as name says, guard ring. So if this is the P region heavily doped and this is the N region second layer, so in between them, if I add a lightly doped P region, so that will avoid the deep penetration to the further region. So that is nothing but a guard ring. So if I add a one more layer for the particular region, then we can avoid the deep penetration to the further region. So this is the for example, in general, what they will do, in order if one region is heavily doped and another region is lightly doped, in that case, in order to get a ohmic point, proper ohmic point, what they will do in their actual fabrication, for example, if this is a P plus region and this is a N region, so along with that N region, they will add one more heavily doped N region of the same type, in order to avoid the deep penetration and to get a proper ohmic contact. Ohmic contact is nothing but a lead points from which we can use this diode. Understanding, no, this one? If I consider the same P layer over here, that is a P plus, and this is my N layer, in order to avoid a deep penetration and to get a ohmic contact, that is a lead point at the both side, what they will do, so same material, that is a N material of heavily doped layer, they will add to get this lead connection. That is what explained over here. P plus N region, again one N plus region, in order to avoid the deep penetration as well as to get the ohmic contact for the particular region. And here it shows the zero bias condition for the one more added N plus type of a region. So this is the heavily doped P plus region and a N region. In order to get a ohmic contact, they will add one more P plus region over here. So if the depletion region penetrate deeply throughout this area, means we will be having one more layer. So like you can see over here, this is a P plus region and N plus region, this is a width that is covered by heavily doped P region. So in order to get ohmic point, so I should have N region, no, but this P plus region, it will penetrate deeply towards the N region. So for that reason, there won't be any ohmic contact. For that reason, they will add a N plus region to get a P as well as a N leading points. Ohmic points are nothing but lead points. So this is the energy band graph of particular P plus and N plus region. So by this it will complete the part A of the module 2, rectification. We will revise quickly whatever we studied till now in the rectifier topic. So rectifier is nothing but a unijunctional device, that is nothing but a diode. So one application of a diode itself is a rectification process. So if a diode is forward bias, we call it as a short circuit. If a diode is reverse bias, we call it as a open circuit. If it is conducting, means resistance is minimum and voltage is minimum and current will be more. If it is not conducting means resistance is more and voltage is more and current will be 0. Here V naught or E naught we call it as a offset voltage, that is a junction voltage. If we know this concept, then we can draw all 4 graphs. So last one is a actual graph. So after that we studied about the application of a PN junction, that is one is a wave shaping and second one is the rectification. So rectification process, we get a pulsating DC. In order to get a pure DC, we supply that pulsating DC to the filter, then we will get a pure DC. So the next point in the same topic is factors affecting the performance of rectifier, that is band gap. First factor is band gap. So band gap is a gap between the valence band and a conduction band. So that will play an important role in rectification process. So here silicon is having a more band gap compared to the germanium. So if a band gap is more, then we need to apply the more supply voltage. So that type of diodes which we operate at higher voltage, higher power, we call it as a power diodes. Then the second concept is device dimension will also play an important role in rectification process. So if a device is lightly doped and one part is heavily doped, means the resistance will vary. The resistance which is having more in one region, so there will be I square R losses will be there. In order to avoid that losses, we need to modify the dimension of particular diode. So this is the theory of entire thing that is shifted over here. So the third factor is again the doping concentration. Because of that doping concentration, we will be having a punch through effect, as well as because of this punch through effect, what happens? A premature breakdown. How we can avoid this premature breakdown? By beveled edge, and second one is by guard ring. Beveled edge is nothing but it won't be in a rectangular shape like a it won't be in a rectangular shape, it's like a trapezoid. So trapezoidal shape. So that shape you can see over here. If we have a trapezoidal shape, then the area at one layer will be higher compared to that one. So that penetration we can avoid. That is a punch through effect we can avoid. If a punch through effect is avoided, then a reverse voltage breakdown will take at the particular value which is specified by the manufacturer. And the second one is a guard ring. So guard ring is nothing but adding one more layer in between the 2p and n layer. So that also the one method of avoiding a punch through as well as a premature breakdown. So these three factors we need to consider. So and more thing, the fabrication is explained over here, how we manufacturer actually fabricate the PN junction diode. So they will add one more layer. If it is a moderately doped, both layers are moderately doped, they will use the lead points for the connection purpose. If one region is highly doped compared to the another region, at that point because in order to avoid because of the effect of punch through, so they will add one more heavily doped region. If a P plus and N region is there, means they will add one more N plus region at the end. So that is explained over here by connecting actual resistance with the reverse voltage. So this is about the rectifier topic. So this completes a part A of module 2.